Hey guys, so the problem we'll analyze now is a problem that we have discussed before, but now we're gonna change something in it. We have again two masses, right? And there is a pulley over here, right? And then there's another mass hanging. Okay. Now what we're gonna do is we are gonna assume that this pulley is massive, okay? And since the pulley is massive, it has a moment of inertia, right? We'll assume that the pulley is a disk, right? Let's assume that the mass of the pulley is mp. So for a disk, the moment of inertia is half mp the r squared. Okay, that's usually given in a question. So let's call this mass A and this B. Okay. So let's look at the forces acting on these masses. Now the difference from before is that the tension in these two parts of the strings are going to be different. Okay. When the pulley is massless, the tensions are the same. Okay. When the pulley is massive, then it is rotating and it is going faster as it rotates, right? So then there is a net torque acting on the pulley. So there is angular acceleration. So the tensions have to be different so that there is a net torque acting on the pulley. Okay, so let's call this tension TA. Okay, and TA is going to be this way. Okay, on the pulley, and TB is over here, and TB is going to be this way over here. Okay. Now let's look at the forces, the other forces. We're still assuming that this is frictionless, so no friction. Okay. Now the weight WA again, and then normal force A, and then for this guy weight WB. So the system is still moving in this direction. This is acceleration of the system. Okay. Now this constraint still holds. The acceleration is the same because the string is still inextensible. Again, it's not like a rubber band, so the acceleration, if this guy moves a certain distance in a certain time, this is gonna move the same distance in the same time. So the acceleration is the same. Okay. So let's look at the equations for these guys. Okay. So let's look at the mass MA. So for MA, so again the vertical direction is trivial over here. Normal force is equal to the weight, okay, of the mass A. Okay, so let's look at the horizontal direction only. So in the horizontal direction, this is actually, the equation is similar to what we did before. Okay, so TA equals MA times A. For mass B, let's draw three lines over here because we have the pulley. So for mass B, you get, now there's of course the vertical direction in this case. So it's moving down, so this force is greater, so you get WB minus T equals MB times A. So WB minus TB equals MBA. Okay, and let's look at the pulley now. That's the tricky part. Okay, you should be familiar with the concept of torque. So on the pulley, the pulley is rotating this way, clockwise, right? This mass is moving down, so the pulley will rotate clockwise. This is the direction of rotation. Now this torque is of course greater than this, the torque by this. So now let's look at let's stick with the convention first. So TA applies clockwise torque, and TB applies a counterclockwise torque relative to the center of the pulley. So clockwise torque gain is what? Is negative. Okay. So TB. So let's write TA first. Okay. So TA times R. Okay. TA times R. So this is the R is the radius of the pulley because the force is being applied on the edge of the pulley. So R is the radius of the pulley. TA times R minus TB times R. Okay, again, the torque due to TB is clockwise. Okay, it's clockwise, and due to TA is counterclockwise. So this is equal to I alpha. Now, not only I alpha, there's a negative sign. Let me just stick that in. Okay, why this negative sign? It's because the pulley, the angular acceleration of the pulley is negative. Okay, clockwise, the pulley is rotating clockwise. So clockwise means that W is, if you use the right hand rule, pointing to the page. So omega is negative. So and if it's speeding up, then alpha and omega point in the same direction. So alpha is also into the page. Okay. So that's the tricky part that's new in this problem. Okay, for the pulley. So the equation for the pulley is therefore TB. You can multiply minus on both sides. You get TB minus TA times R equals I. Now, instead of writing alpha, what I'll do is I'll use this equation. So remember that tangential acceleration is equal to alpha times R, and alpha is therefore A divided by R. Okay, so you get A over R over here. Okay, so now let's solve these three equations. Let's call this guy equation, this equation 1, this equation 2, and this equation 3. Now you have to solve these three equations. So let's first add 1 and 2. Okay, so add 1 and 2. So we get WB plus TA minus TB equals MA plus MB times A. Okay, and that gives now you can plug in TA minus TB, right? So TB minus TA is IA divided by R squared. You can bring this R in the denominator over here. Okay, so TB minus TA is plus IA over R squared, and TA minus TB will be minus. So you get WB minus IA over R squared equals MA plus MB times A. Okay, so so now you can what you can do is solve this. You can write this as WB. Okay, just this. So you get WB equals I over R squared plus MA plus MB times A, and A is therefore WB divided by MA plus MB plus. Now I over R squared, I is the moment of inertia of the pulley, so I over R squared is half of MP. Okay, so you get half of MP over here. Okay, so that's your acceleration. Okay, for this system. Now let's assume some numbers for the to get an answer. So let's say that MA is equal to 12 kilograms. MB is equal to 5 kilograms, and MP is equal to 2 kilograms. Okay, so you notice that I don't need the radius of the pulley. Okay, so I just need these masses because the answer is in terms of the masses. So acceleration is equal to MB times G divided by MA plus MB plus half of MP. Right. Now if you plug in the numbers, you can do that. So MB is just 5 kilograms, and this is 9.8 meters per second squared. So this is MA plus MB plus half of MP, so that's 17, and that's half of this is 1, so you get 18. So you get 18 kilograms in the denominator. So the answer turns out to be 2.72 meters per second squared. So that's your acceleration of the system. Okay. Notice that if the mass of the pulley is 0, you get the expression we derived before. So the pulley is so the pulley modifies the acceleration of the system. Okay. And now if you want the tension in the system, you can use these equations. Now the tensions are different, right? So you can use 1 and 2. So TA is MA times A, so you can find the tension. So MA is 12 kilograms and A is 2.72 meters per second squared. So you get, for tension, you get 32.6 newtons. That's your tension TA. For TB, so this was equation 1. You can use equation 2. So TB is WB minus MB times A. So you get WB minus MB times A. Okay. So WB is MBG. Okay, this is MB times G. So you get MB. You can take MB common, so you get G, MB times G minus A. So now you plug in the numbers, you get 35.4 newtons. So this gives you a feeling of the numbers. So this was the masses connected with a string with a massive pulley. Hope you liked the video. Please, if you have any questions, post them in the comments, and like the video if you liked it, and please subscribe. Thank you for watching.